Welcome to Solubility Equilibria and the Solubility Product. So, let's consider a saturated solution of barium sulfate in contact with solid barium sulfate. So we can write an equilibrium expression for our dissolving process of the slightly soluble solid barium sulfate. So we have barium sulfate solid, dissociates to form barium ions and sulfate ions, both aqueous. Because our barium sulfate is pure solid, then the equilibrium expression depends only on the concentration of our ions. So we start out with our Kc there. Kc is equal to the concentrations of our products divided by the concentrations of our reactants. And because the barium sulfate is a solid, we consider its concentration to be constant, and thus we can drop it out of our equation. So the Kc there is equal to barium concentration times the sulfate ion concentration. This is a special equilibrium because this represents the dissolution of our barium sulfate. So we're going to give this Kc a special symbol and special name. The name we're going to give it is the solubility product constant, or the solubility product. We're going to call this Ksp. So for barium sulfate, Ksp is equal to barium ion concentration times the sulfate ion concentration, and it happens to have at 25 degrees C a value of 1.08 times 10 to the minus 10. So in general, our solubility product is equal to the product of our molar concentration of ions raised to the powers corresponding to their stoichiometric coefficients. So we have species A, we have a subscript little a, species B bonded to it, subscript little b, and our little a and little b there are going to be the same as on that side. So our Ksp is concentration of A raised to the little a power times concentration of B raised to the little b power. So solubility then is the amount of our substance that dissolves to form a saturated solution. And generally we express it in terms of grams of solute that will dissolve per liter of solution. So it's in grams per liter. So molar solubility is the number of moles of solute that dissolve to form a liter of saturated solution. So it's basically the number of moles per liter that we can get dissolved. So again, solubility is referring to mass, so grams per liter. Molar solubility is referring to moles, so moles per liter of a saturated solution in both cases. So if you're asked to calculate the solubility of a substance, what units should your answer have? And if you're asked to calculate the molar solubility of a substance, what units should your answer have? I want you to pause the video and write down what your answers to these two questions are. In the first one, if you're asked to calculate the solubility, your answer should have units of grams per liter. If you're asked to calculate the molar solubility, your answer should have units of moles per liter. So be careful on solubility versus molar solubility and what the question is asking you to find. So we can use the solubility to find Ksp and vice versa. So if we want to convert from solubility to Ksp, we want to convert solubility into molar solubility via the molar mass, and then convert molar solubility into the molar concentration of ions at equilibrium via our equilibrium calculation, and now use our equilibrium concentration of ions in our Ksp expression to calculate the value of Ksp. So let's look at an example. So if we want to calculate the solubility product of lead 2 chloride, if 50.0 milliliters of a saturated solution of lead 2 chloride contains 0.2207 grams of lead 2 chloride, we know the dissolution process involves our lead chloride, lead 2 chloride going to lead 2 ions, and chloride ions. We know the solubility product looks like this, and again we can drop out our lead chloride because it's a solid, so Ksp there is equal to the concentration of lead 2 times the square of the chloride ion concentration. So now we want to convert our mass, 0.2207 grams of lead 2 chloride in 50 milliliters, into a molar solubility. So we know we have 0.2207 grams of lead chloride. We're going to divide that by the volume, 50 mils. We want to convert from grams of lead chloride to moles of lead chloride. 1 mole of lead chloride is 278.1 grams. And we want to convert our volume here from milliliters into liters. And that gives us a lead chloride concentration of 0.0159 molar. So the next step is then to do our equilibrium calculation. So we start out with our ice table. So we've got our lead chloride that's dissolving to give us lead 2 and chloride ions. We start out, we have some solid. We don't care what the change is because we just end up with less solid. We start out with no lead 2 in solution and no chloride in solution. If we dissolved 0.0159 molar, that means that we're reducing our amount of lead chloride by 0.0159 molar. We're increasing the concentration of our lead 2 by 0.0159 molar, and we're increasing the concentration of our chloride because we're forming 2 chlorides for every lead. We need to double that value here, so 0.0318 molar. And then at equilibrium, well, we have less of our solid, but the value is still, the concentration is still whatever value it is. The concentration at equilibrium of our lead 2 is then 0.0159 molar and 0.0318 molar of our chloride. Now we can substitute our equilibrium concentrations into our KSP expression. So we have KSP equals a lead concentration, which we know is 0.0159 molar. We times the chloride concentration squared, so we need to square our 0.0318 molar. And when we work out the math, it ends up being 1.61 times 10 to the minus 5 molar cubed. So that was converting from solubility to KSP. And remember, solubility and molar solubility are different. But if we want to go the other way and go from KSP to solubility, if we're given a KSP value and we want to find out how much of our substance dissolves, what mass of our substance dissolves, we need to follow these steps. So first, we'll write out the KSP expression. Then we'll let X equal the molar solubility of our salt. We'll use the stoichiometry of our reaction to express the concentration of each species in terms of X. We'll substitute these concentrations into our equilibrium expression and then solve for X. And then this calculation works best for salts whose ions have low charges. When you increase the charges on the ions, the calculations start to become less ideal. So let's look at an example. If we want to calculate the solubility of silver chromate in water, if the KSP is 1.1 times 10 to the minus 12. So first we'll write out the equation and the equilibrium expression. So silver chromate dissolves to give us 2 silver ions and 1 chromate ion. We have the KSP is equal to the square of the silver ion concentration times the chromate ion concentration. Then we make our ice table. We start out with solid silver chromate. We're going to dissolve X amount of it, and we end up with less of our solid. We don't care how much. As long as we don't react away, as long as we don't dissolve all of our solid. We start out with none of our silver ions. We're going to add 2 silver ions for every 1 silver chromate formula unit that dissolves, and that means that we'll end up with a concentration of 2X for silver. We start out with no chromate ions. We're going to add plus X, and that means that our concentration at equilibrium is X. So now we're going to substitute in our equilibrium concentrations into our KSP, and our KSP into our equilibrium expression, and then solve for X. So here's our KSP expression. We're going to plug in the KSP value of 1.1 times 10 to the minus 12. We're going to plug in 2X for silver. Remember that you've got to square it. And we're going to plug in X for the chromate ion concentration. So 2X squared times X is 4X cubed. That's equal to our 1.1 times 10 to the minus 12. We're going to divide 1.1 times 10 to the minus 12 by 4 to give us X cubed is equal to 2.8 times 10 to the minus 13. Then we'll take the cube root to give us X is equal to the cube root of 2.8 times 10 to the minus 13, which is 6.5 times 10 to the minus 5. what sorts of factors affect the solubility? We have three factors that have a significant impact on solubility, and they are the presence of a common ion, the pH of the solution, if if one of our ions involved is an acid or a base, and also the presence or absence of complexing agents, which are also called chelating agents or ligands. So let's look again at the common ion effect, which we've already seen a little bit in chapter 15 with acids and bases. So the solubility of a slightly soluble salt is decreased when a common ion is added. So again, this is another application of Le Chatelier's principle. So let's look at the solubility of calcium fluoride. We have calcium fluoride. When we dissolve it to give us calcium ions and fluoride ions, if we add more fluoride by adding some compound containing fluoride, like sodium fluoride, then the equilibrium is going to shift. And as we add more of our product, Le Chatelier's principle says the equilibrium shifts to the left to try to minimize that stress. Which means if we add more fluoride, then the solubility of calcium fluoride goes down because we can get less of our calcium dissolved to offset this increase in fluoride concentration. So when we do that, if we started out with a saturated solution, if we add more fluoride, then we're going to precipitate out some calcium fluoride. So some solid calcium fluoride is formed and precipitation occurs. And as sodium fluoride is added to our system, then the solubility of calcium fluoride decreases. So if we add a common ion, the solubility is going to decrease. So in general, the solubility of a slightly soluble salt is decreased by the presence of a second salt that produces a common ion. That's what we're going to say is the common ion effect. So let's look at an example. Let's calculate the solubility of barium sulfate in a 0.020 molar sodium sulfate solution. So we're not putting barium sulfate into pure water anymore. Now we're putting it in a solution that already contains 0.02 molar sodium sulfate. So the sodium isn't going to make a difference, but the sulfate here from sodium sulfate is our ion in common with the barium sulfate. So the product, the solubility product at KSB for barium sulfate is 1.1 times 10 to the minus 10. And then we're going to start by writing out the reaction and the equilibrium expression. So barium sulfate dissolves to give us barium ions and sulfate ions, which we can write then the KSP is equal to barium ion concentration times the sulfate ion concentration. We'll make our ice table. So we start out with our solid. We're going to dissolve away X amount of it. We'll have less solid left. We start out with none of our barium ions in solution. We're going to dissolve X, which means we'll have X left. But now, instead of having 0 here for sulfate, we already had some sodium sulfate in solution. So our sulfate ion concentration is initially 0.020 molar. We're going to add X to it, however much of our barium sulfate dissolves. And that means that down here, we have 0.020 molar plus X. And we no longer have X and X. So now we're going to substitute these equilibrium concentrations into our equilibrium expression. And then the KSP is equal to barium concentration times the sulfate concentration. The barium concentration is X. The sulfate concentration is this 0.020 molar plus X. And then when we distribute the X through, we get 1.1 times 10 to the minus 10, that's the KSP value, is equal to X squared plus X times 0.020 molar. And now we have two options for solving this for X. We can either use the quadratic formula, so X is equal to opposite B plus or minus square root of B squared minus 4AC all over 2A, or we can make a simplifying assumption. So let me point out that if you use the quadratic formula, it works, always. You are, however, going to get two results. You're going to get a result from the positive here and from the negative. One of them will be ridiculous. It will either be a negative value, and you can't have a negative concentration because you can't have less than nothing, or it will be a value that is higher than what you originally started with. If we started with some amount, let's say we start out with 1 mole of barium. If you react away 1.5 moles, well, that's a ridiculous result. You can't physically react away more than what you had to start with. So one of the two answers will always be ridiculous when you use the quadratic formula. And if you have a calculator, I would recommend that you just do this method, as long as you can do the math correctly, punching it into your calculator. Right. The second way is to make a simplifying assumption that removes one of the x terms and makes it easier for us to do the math. So we have to rearrange our quadratic equation to get all the terms on the right and set them equal to 0. So here we're using the quadratic formula method. So 0 is equal to x squared plus 0.020 times x minus 1.1 times 10 minus 10. So we can plug this in for our quadratic formula, where 1, the unwritten 1 there on the x squared, is a, b is 0.020, and c is negative 1.1 times 10 to the minus 10. Make sure you include whatever sign there is on your term. So we plug it in, do some math, and we end up with two results. One is 5.5 times 10 to the minus 9, and the other is negative 0.0200000055. This negative concentration is obviously our ridiculous value. We can't have a negative concentration. We can't have started out with no barium ions in solution and react or dissolve a negative concentration, because a negative concentration of dissolving barium ions would mean to be precipitated. So we don't have any barium ions in solution to precipitate, so we have to throw that one out, which means that this one is our answer. Again, our second solution here doesn't make sense because we can't have a negative concentration. So our concentration of barium ion is 5.5 times 10 to the minus 9 molar. So here's our second method. So that was our first method using the quadratic formula. And if you have a calculator, that's the method that I would recommend you using. But the second method here makes a simplifying assumption. If x is small, which means less than 5%, compared to our initial concentration of our common ion, our sulfate ion, then we can assume that the concentration of the common ion, the sulfate, doesn't change significantly. And this means that we assume that our sulfate ion concentration stays at that 0.020 molar. And that simplifies this because now this x term that was over here, 0.020 molar plus x, that plus x is gone. As long as that plus x is small compared to this value, then we can ignore the plus x. And that means that now when we plug it in, we have a rather simple equation. We can solve that for x and plug in our values, and we get 5.5 times 10 to the minus 9. That's the same value we got the other way. So now let's check. 5.5 times 10 to the minus 9, is that small compared to 0.02? Well, 0.02 is 2 times 10 to the minus 2. This is 5 times 10 to the minus 9. So we've got 7 orders of magnitude in between. This is far, far lower than 5% of that. So our assumption is fine. And again, here I've done the math. So again, we have to check to make sure that x is less than 5% of our initial concentration. X was 5.5 times 10 to the minus 9 molar. Our initial concentration is 0.02 molar multiplied by 100%. That gives us 2.75 times 10 to the minus 5%. So that's much, much less than 5%. So our assumption is valid here. So let's look at how solubility is affected by pH. And again, we're going to apply Le Chatelier's principle. So let's consider the solubility of magnesium hydroxide. So we've got magnesium hydroxide solid. It's going to dissolve to give us magnesium ions and hydroxide ions. So if the hydroxide ion is removed, then our equilibrium will shift towards the right and more magnesium hydroxide will dissolve. Which means if we add an acid, if we lower the pH, then we'll effectively be removing hydroxide ions from solution as we make water, and more of our magnesium will dissolve. Because as we remove some hydroxide ions, Le Chatelier's principle says this equilibrium shifts to the right, so we get more of our solid to dissolve. If, on the other hand, we add a base and raise the pH, then we're increasing the concentration of hydroxide ion, and that's going to shift the equilibrium to the left. So magnesium hydroxide is going to have a lower solubility at high pH and a higher solubility at low pH. So again, hydroxide ion can be removed by adding a strong acid. when we reacted with hydrogen ions from our strong acid giving us water, and that means that as pH decreases, our hydrogen ion concentration increases, hydroxide ion concentration decreases, and this will then increase the solubility of our magnesium hydroxide. Let's look at another example. If we have calcium fluoride, and we want to calculate the solubility, so we've got calcium fluoride, that dissolves to give us calcium ions and fluoride ions. If we remove some of our fluoride ions, then our equilibrium will shift towards the right, and our calcium fluoride will dissolve. So we can remove some of our fluoride ions by adding a strong acid, because remember that hydrofluoric acid is a weak acid. So fluoride plus hydrogen ions will give us HF, hydrofluoric acid, and as pH decreases, then the hydrogen ion concentration increases. This equilibrium shifts to the right, removing some of our fluoride ions from solution, because now they're in the HF form, they're protonated. So our fluoride ion concentration decreases. This increases our solubility of calcium fluoride, because again, we're removing some of our fluoride, and that means that this equilibrium will shift to the right. So that was solubility, equilibria, and the solubility product.